Good morning, everyone. You are welcome to today's lecture on atomic physics. We are going to be looking at the concept of half-life. It will be twofold. One, we have to discuss the conceptual understanding, and number two, we're going to look at the computational and manipulative skills that are associated with half-life. As you can see on the board, the half-life of a radioactive or unstable nuclide just has to do with the time it takes for half the initial amount of the radioactive nuclide to disintegrate. Some other persons will put it conversely. They will say this is the time it takes for half the original or initial amount to remain. So whichever way you look at it, the half-life is just the time it takes for an unstable nuclide, for half of the unstable nuclide to disintegrate. Basically, that's half-life. Thank you. Good morning, everyone. You are welcome to today's lecture on atomic physics. We are going to be looking at the concept of half-life. It will be twofold. One, we have to discuss the conceptual understanding, and number two, we're going to look at the computational and manipulative skills that are associated with half-life. As you can see on the board, the half-life of a radioactive or unstable nuclide just has to do with the time it takes for half the initial amount of the radioactive nuclide to disintegrate. Some other persons will put it conversely. They will say this is the time it takes for half the original or initial amount to remain. So whichever way you look at it, the half-life is just the time it takes for an unstable nuclide, for half of the unstable nuclide to disintegrate. Basically, that's half-life. Thank you. Dear students, we're going to continue with a number 2 question. Remember that if you are exposed to a sufficient number of graded exercises in any mathematical based subject, you get better, you get good at it. Alright, so we continue our lectures on the computational aspects of half-life with the second question. On the board, we have a question that says a radioactive substance has a half-life of 2 years. If the initial mass of the substance is 320 grams, calculate the quantity of the substance that will remain after 6 years. Let's do the analysis. What are we given? The given. A radioactive substance has a half-life of 2 years. T, the half-life, is 2 years. If the initial mass, that's your A, the initial mass, A, is 320 grams. Calculate the quantity of the substance that will remain. Obviously, that is in reference to Q, the quantity remaining, after the given time. After, that underscores the given time, after a given time of 6 years. Again, our formula, exponential decay formula, will come in handy here. Q is A times 2 raised to the power minus N over T. By now, the formula should be getting so used to you that you could almost write it from your memory, off the top of your head. Q is what we're looking for. So it's a straightforward question this time. A is given to us as 320 times 2 raised to the power. Our N is 6. And the half-life T is 2. So what do we have here? We have 320 times 2 raised to the power minus 3, because 6 divided by 2 is 3. I told you to get familiar with the common fractions like 1 over 2, 1 over 4, 2 raised to the power minus 3. 2 raised to the power minus 3 is actually 1 over 8. 2 raised to the power minus 3 is 1 over 8. And so we now have 320 divided by 8. That's 320 divided by 8. And 320 divided by 8, that should be around 40. So that is the remaining amount will have 40 grams left after 6 years for the substance with a half-life of 2 years and an initial amount of 320 grams. So this is the remaining amount, 40 grams of the substance. That's a good one. Okay, students, we have another question on our board to further elucidate this concept, the mathematical and computational aspect of half-life. It says a radioactive substance of mass 768 grams. I'm going to delve straight into our analysis. The given. What are we given? We have the initial amount, A, as 768 grams. Has a half-life. We're told very clearly that the half-life T is 3 years. After how many years? The required time. After how many years? That's N, our required time. We're looking for N. After how many years does this substance leave only 6 grams undecayed? If you say 6 grams undecayed, that's the remaining amount. So it therefore translates to the fact that Q is equal to 6 grams. We have been using a particular formula. It's called the exponential decay formula, and it's written as Q equal to A times 2 raised to the power minus N over T. And we're going to employ this once again for this question. 6, I'm imputing the data, is equal to 768 times 2 raised to the power minus N over T. If I divide both sides by 768, I'm going to have 6 divided by 768 equal to 2 raised to power minus N over T is given as 3. Yes, T is 3, so we should have imputed our 3 here. Okay, so 6 divided by 768 gives us 1 over 128. And this is equal to 2 raised to the power minus N over 3. Again, about this fraction, I've told you, you have to try and get yourself very well acquainted with these common fractions. 1 over 128 is obviously 2 raised to the power minus 7. So 2 raised to the power minus 7 is equal to 2 raised to the power minus N over 3. This will take out this. And we're going to have at this point, 7 is equal to N over 3. So the given or required time will be 7 times 3, and that is 21 years. It's going to take 21 years for this particular radioactive source to decay to 6 grams from 768 grams. All right, students, we have a final example here. It says a nuclear reactor produces 20 kilograms of uranium-235. If the half-life of the uranium is about 70 years, how long will it take to decay to 0.1 kilogram? In your analysis, first note your data. What are you given? The nuclear reactor produces 20 kilograms of uranium-235, that's fissionable uranium. The initial amount is 20 kilograms of the reactor fuel, that is uranium-235. If the half-life, that's T, is about 70 years, so I have to assume 70 years as the half-life, how long will it take? Again, required time. How long will it take to decay to 0.1 kilogram? So the remaining amount, the remaining count, is now 0.1 kilogram. The formula is Q equal to A times 2 raised to the power minus N over T. Q is 0.1 and A is 20 times 2 raised to the power minus N divided by, our half-life is given as 70 years. I'll divide both sides by 20 and we're going to have 0.1 divided by 20 equal to 2 raised to the power minus n over 70. 0.1 over 20 is like having 1 over 200. I can write it as 1 over 200, which is equal to 2 raised to the power minus n over 70. This question is particularly very interesting because I needed you to be aware of the fact that not every occasion that you have these very common fractions that you can just express exponentially with a base of 2. It will not always be the case. So if you are confronted with such trick question that does not follow the trend, because it bucks the trend, it doesn't follow the normal trend, how do you handle this? Your mathematical skill to your rescue. You apply the natural log to both sides. You put ln to both sides, the natural log to both sides. So ln 1 over 200 is equal to ln 2 raised to the power minus n over 70. So this is going to be ln 1 over 200. Actually, where I'm using the ln, the natural log, you could also use a normal log as well to both sides. So ln 1 over 200 is now minus n over 70 into ln 2. You know, from your laws of logarithm, the power can become a coefficient at the front like this. So you now have minus n over 70 into ln 2. If you solve on, you're going to have ln 1 over 200 is actually minus 5.2983, and ln 2 is the more common one. You have your minus n over 70, of course. Ln 2 is 0.693. So if you go ahead to solve for your given time, you're going to have 70 times minus 5.2983 divided by minus 0.693. Of course, you will notice that I sent the 70, I transposed the 70, and negative 0.693 so that I could have n as the subject of the formula, making n the subject of the formula. And we're going to have our answer to be approximately equal to 535. 535 years. 535 years. 535 years. So my dear students, I need you to be very careful and deliberate when you try to practice this. In lieu of the ln, you could have used your normal logs, log, that's log to the left and log to the right, because that's what I did. I applied the natural log, ln, that's log to this e, to both sides. If you do that, at the end of the day, you can have your n as 535 years.